Good morning, everybody. Welcome to another exciting morning of Chem 1211 with your host, me, Dr. White. Notice I do that in unison. I practiced that. Anyways, good morning, everybody. Let me give you the game plan. Today, I'm going to talk about the lab that's due today because there was some misunderstanding, which hopefully I've cleared up. And then we'll go through the gas problem set, and then we'll do the molarity lab. And then I'll say goodbye and you can run away. But until then, I've got you. All right, let me just open up something which I didn't have opened up. All right, those of you who don't have your webcam, use your emoji. Thumbs up, people. Do you see the ideal gas? Thank you. All right. Based on my office hour Wednesday night, a number of you were confused by my lab. I'm sorry. I didn't see that kind of confusion last semester. Same lab, but guess what? It still caused confusion. I'm still sorry. So I straightened it up. And where I straightened it up, didn't change anything. Where you see now letters, I had like number one, number two, and all that. And people got confused with the number here and the number here. Well, I've clarified that. Nothing has changed other than instead of numbers, I'm now using letters. K and K, that might be confusing. Or no, it's actually G. Anyways, well, you can't get everything right. And this should make your calculations easier to do. Now, if you've already handed in your lab and you're happy with it, that's fine. If you've already handed in the lab and you want to go back and look at it, I've changed the downloads for that lab. You have until Sunday to look at the new lab and see if you need to make any changes. And that's that. Any questions about that? All right, before we go on to the gases problem set, it's time for a quick public service announcement from me, your host. Don't forget, next Wednesday is test three, test three, oh, test three, and be sure to study. Best way to study, do the practice problems. Also, you can go back and look at the videos for any parts you're having difficulty with. On Monday, I will go through the solutions problem set in Zoom lecture. Make sure you try them before then in case you have any questions. And with that, any questions? My camera's up here. Not, I wish it was down there because my control on the screen is down here. All right, let's get to work. All right, thumbs up, people. Do you see important information on your screen? Thank you. All right. And the reason I do that is Zoom tells me you're seeing the screen, and half the time you're not unless I ask. When I don't ask, you usually aren't. All right. If you go to the lecture section of Blackboard, you'll see a file near the bottom, important information test number 3. I'd highly recommend you look at that because these are things you don't have to memorize. You'll be given this. And if you notice, I have a whole section on gases. And the first thing I'd like to show you is 760 torr equals 760 millimeters of mercury equal 1 atmosphere. Also based on this, 1 torr equals 1 millimeter mercury. These are all exact numbers. All right, let's go up here. And now let's look at a couple of problems. I better make these a little larger. Thumbs up, people. Can you see Chapter 7 gas law? Thank you, Justin. And all the rest of you too. And if we look at number 1, how many torr is 41.5 millimeters of mercury? Well, you're trying to find torr. You're given millimeters of mercury. And now here's your millimeters of mercury. Here's the torr. And you use your good buddy, your good friend, unit analysis. Whatever you're trying to get to goes on top. Whatever you're trying to get rid of goes underneath. And as I said, you could put either 760 over 760 or 1 torr, 1 torr. There's 3 significant figures. Your answer is 3 significant figures. Now let's look at number 3. How many ATM is short for abbreviation for atmospheres? That's the measure of pressure, is 741 torr. Torr is honoring the great Italian scientist Torricelli, who did a lot of work in pioneering our understanding of gases. So what are we trying to find? Atmospheres. What are we given? 741 torr. This is where we start. This is the units we're trying to get to. Whatever we're trying to get to goes on top of the ratio using your good buddy, your good friend, unit analysis. Whatever we're trying to get rid of goes underneath. Where do we get these numbers? As you saw in important information, I also wrote it here too for you. 760 torr equals 760 millimeters of mercury equal 1 atmosphere. And these are exact numbers. So 1 atmosphere per 760 torr. Torr cancel out, 3 significant figures, 3 significant figures. And I'm going to share the fun with you today. And why don't you try this one? How many torr is 9.876 atmospheres? Your turn. Oh, excuse me. If you don't have your calculator, just set it up. And when you're done, don't forget to give me a thumbs up. If your camera's not on, use the emoji. I wonder who came up with that word. Why don't they call it symboli? Notice how Zoom doesn't have a thumbs down. I'm going to start a new company. emoji apps for Zoom. If I thought of it, I bet there's someone out there who's doing that already. It's too obvious. All right, everybody done? All right, let's get going. What are we trying to find? How many torr? What are we given? 9.876 atmospheres. Well, this is the only thing I have to start with, so I'm going to start with that. If I have a ratio, what units do I want my answer to be? Well, we figured that out. Torr. And now it's time to use your good buddy, your good friend, unit analysis. Whatever we're trying to get to goes on top of the ratio. Whatever we're trying to get rid of goes underneath. Where do we get those numbers? Well, first of all, let's put this in. Where do we get a relationship of torr to atmospheres? Right here in important information. 760 torr is equal to 1 atmosphere. Both of these are exact numbers. Therefore, this is 4 significant figures. Our answer should be 4 significant figures. Notice atmospheres divided by atmospheres cancels out because anything divided by itself equals number 1, cancels out. And now I can open up my calculator, hang in there. And I get this number. And if I were to take it and put it in scientific notation, which I think most of you are going to do on your calculator, and here we have this in scientific notation. And the question is, how many significant figures? Well, 4. Over here in A1, why don't you first, and then I'll do it, round that off to 4 significant figures. That practice is good for you. Time's up. Keep the 7, keep the 5, keep the 0, keep the 5. That's my 4 significant figures. Use the 7 to round off. Is that 5 or higher? Yes. So I'm going to drop everything and increase the 5 to 6. So that would be 7.506 times 10 to the third. Let me write it here. And that's how you do it. Hint, you should know how to do this. All right. And the rest of these are just more examples of doing the same thing. Now, let's look at number 6. By the way, anytime during this time, if you want me to stop and look at a specific problem, ask. Because as always, there's no such thing as a dumb question in my class, and all questions are good questions. And I answer them too. How about that? All right, let's look at number 6. If a balloon has a pressure of 658 torr, that's a pressure, and a volume of 1.894 liters volume, what is the pressure of the balloon if the volume is increased to 5.133 liters? Now, if you notice here, we're talking about a gas. because we're talking about pressure and volume. And it's the gas problems. Duh. But anyways, the only thing we're dealing with is pressure and volume. As soon as you see that, you know it's Boyle's law. And if you look over in important information, test number 3, Boyle's law. P1 times V1 equals P2 times V2. P1, initial pressure. Hold on 1 second. Maybe more than 1 second. There, squiggly blue lines are gone. All right, P1 is the initial pressure where you started that pressure. V1 is the initial volume where you started. What's your initial volume? Then P2 is your final pressure where you end up, and V2 is your final volume where you end up also. These pressure and volume can be in any units. And therefore, if we look at this, what are we being asked to find? What is the pressure, which is after you make a change, P2. The initial pressure is 651, 658, yeah. And that's P1. The initial volume is here, that's V1. And then after you increase it, that's the final volume, V2. Well, we have P1 equals V1 times P2 equals V2. And hold on 1 second. And we're trying to find P2. And how do you solve this equation for P2? You get it alone on one side. So how do you get rid of V2? Well, anything divided by itself equals the number 1, essentially is gone because 1 times anything is that anything. So P2, to get rid of V2, I'm going to divide by V2. But whatever you do to one side, you have to do to the other side. Now V2 over V2 cancel out. And therefore we have P2 equals P1 times V1 divided by V2. Dr. White likes to write this, you don't have to, but I'll switch it like this. And now this is the equation we use to solve for P2. Now, if we go back to the problem, oh, look, I got it right. And the nice thing about finding out what is P1, V1, and V2 in the beginning is, once you get this stuff done, all you gotta do is plug in the numbers. P1 is this number, V1 is this number, and V2 is this. Now, you can still use your good buddy, your good friend, unit analysis. How? Notice liters divided by liters cancel out the units, and therefore you're just left with torr, which is a unit of pressure, which we're trying to get to. And therefore, we will get to the right answer. Now, when you do a multiplication division, you get the same number of significant figures in your answer, that the number you're multiplying or dividing that has the fewest significant figures, 3, 4, 4. 3 is the lowest, so that's my answer. Now, why don't you look at number 7 and you try it. If a piston has a volume of 22.4 liters at 12.34 atmospheres, what's the volume of the piston when the pressure is reduced to 3.567? let's do the first step. First of all, well, why don't you try it on your own? I'm going to see if you're up to the challenge. I think you are. And remember to help Dr. White out. If you can turn on your webcam, it makes me feel better. It's always good to make the instructor feel better. Did that work? Or should I do guilt on you? Oh, I feel so sad because I can't see your faces. Oi, oi. My mother and grandmother were experts at Jewish guilt. Other societies have that too. I'll try the poll. All right, looks like everybody's just about done. So let's take a look at it. Now, if a piston has a volume of 22.4 liters, that's the initial volume, V1, at a pressure of 12.34 atmospheres. Doesn't say pressure, but you should know ATM is pressure units. So that's P1, the initial pressure. What's the volume, V2, when the pressure is reduced to 3.567 atmospheres? That's P2. So what are we trying to do? Well, it's only pressure and volume. So use Boyle's law, P1 times V1 equals P2 times V2. And what are we solving for? V2. Well, how do I get rid of P2? You divide by that, because anything divided by that becomes the number 1. And 1 times V2 is V2. But whatever you do to one side, you have to do to the other. And I did. And then this cancels out. V2 equals this. I rewrite it. And since I took the time to put these units and discover what's P1, V1, and P2, I can plug them right in. Now, before I go any further, notice the unit atmosphere is divided by the unit atmosphere, and that becomes the number one. And cancels out, and I'm left with liters, which is a volume. And notice this is 4 significant, this is 3, this is 4. My answer is 3 significant figures. And that's how you do it. And the rest of them are further practice like that. All right, let's move on. Now, if you look at important information, test number 3, you'll see the ideal gas law, PV equal nRT. Now, in the ideal gas law, which is Dr. White's favorite mathematical equation in all of chemistry, yep, I like this, is P is pressure, but it has to be in atmospheres. V is volume. It has to be in liters. N is moles. Oh, you know what moles are. And temperature is Kelvin, has to be in Kelvin. And R is the universal gas law constant. And for this class, we're using, for these units, 0.0821. And this is a calculated value. Therefore, R, as I'm giving it to you, is 3 significant figures. Now, common mistake when doing a problem like this, you're never going to be given the pressure in atmospheres. I'll always give you volume in liters. You'll never get moles, you'll get grams, and temperature is Celsius, never Kelvin. If you look up here, notice an important information, in case you forgot, Kelvin equals degrees C plus 273. But before we do a problem, let's look at PV equal nRT. Now, in winter, like we had a couple years ago and back in 95, I'll give you a little story. What happens to the temperature? It gets cold. This winter, we weren't that bad, but we've had some brutal winters here. And back in 95, I think it was, or I think it was earlier than that, somewhere around that. It got real cold, and I was living in an apartment complex, and I didn't have a garage like I have now. And the temperature got real cold that night. And because, and I'll teach you later, when it gets cold, that also affects your battery, and you should drive around. I go out to my car. I have a 4-wheel drive Explorer. The last 2 cars have been Explorers. I like them. And I go and look, and I say, oh no, I've got 4 flat tires because the tires are way down. And it took me about almost a second to think, come on, it's cold, PV equal nRT. And I went over to my local gas station. Back then, all the gas stations had compressors, putting air in your tires, that were free. Right now, around my house, there are only 2 gas stations of the many that are still free, luckily. But anyways, Dr. White's cheap. But anyways, I filled up my tires. I'm pretty quick. I'd say it took me maybe 3 or 4 minutes. And by the time I finished my 4th tire, I look up. When I drove in, there were no cars. When I looked up, there were 10 cars waiting for the same reason. Why? Because in your car tires, you have either air or nitrogen. Don't waste your money on nitrogen. That's my personal opinion. Because air is 80% nitrogen. The oxygen doesn't make a difference if it's in or outside the tire will affect the rubber the same way. But anyways, in your tire, R never changes. If you don't have a flat, which I didn't, the amount of air, moles don't change, and the volume doesn't change. So if PV equal nRT is true, if the temperature goes down, then the pressure has to go down, and that's why it looked like my tires were flat. Now, I think I got my dates wrong. This winter, I think, was somewhere around 1986. But in the summer, what happens to the temperature? It goes way up. And this was 1995. Now that I remember it, that was the summer. It was so tragic. Over 500 people in the Chicagoland area died because of the heat-related issues. And since then, luckily, politicians have set up cooling areas where people who don't have air conditioning, or if your air conditioning breaks down, can go and stay cool and not suffer health problems. And both COD and ECC open up campus to do that, which is a good thing. Well, in the summer, if your temperature goes up in your tires, PV equals nRT, because there's gas in your tires. If you don't have a flat, first of all, R never changes, N never changes, V never changes. Well, if the temperature goes up and PV equal nRT, this whole side has to equal this whole side. And if V doesn't change, therefore your pressure goes up. And what happens if your tires are already full? You get a blowout, just like blowing up a balloon too much. And back then, when it was super hot, I remember it was almost 2 weeks. The daytime temperature was above 102 for almost 2 weeks on the toll road, because back then I worked in a company in Great America, or near Great America in Gurnee. I had a long commute on the toll road. Coming back, you could see cars and trucks over at the side with blowouts, and you could see big pieces of rubber on the road from their tires blowing out. That was because temperature went up, pressure went up. All right, thumbs up, people. Do you see if you burp on the screen? Bet you didn't think you get into burps in chemistry. Well, it is. All right, let's take a look at this. Now, if we look at this, the question is, if you burp 86.75 grams of carbon dioxide, CO2 gas, at 545 millimeters of mercury, 34.6 degrees C, then what is the volume of your burp? Well, first of all, what are you being asked to find? Volume, V. You're given a weight, a pressure, and a temperature. And on the important information, you're also given R. How do I know I need that? Well, if you look at the problem, especially here, you're dealing with a gas. Are any of the variables changing? No. And therefore, you know you should use PV equal nRT. Oh, look, I forgot something up here. It should be 15 points. Why so many? Well, it's a lot of work. And this is one of those problems I highly recommend you show all your work. All right, first of all, let's solve for V. P times V equal nRT. I want V alone, so how do I get rid of P? Divide by P. Anything divided by itself is number one. Whatever I do to one side, I have to do to the other. And I did. Pressure divided by pressure is 1 times V is volume. And then on the side is nRT divided by P. Did I get your attention? I hope I did. All right, listen carefully. What I'm about to tell you, students make this common mistake and get this problem wrong. Don't make the common mistake. Pay attention. Did I get your attention? Let's look at our problem. Now, once you got V equals nRT and P, students will put this in the pressure. No, pressure has to be in atmospheres in PV equal nRT. So I have to convert millimeters of mercury to atmospheres. Use your good buddy, your good friend. Atmospheres go on top of the ratio, millimeters go underneath. Where do you get this? These numbers, important information. I remind you, 1 atmosphere equals 760 millimeters of mercury, and it also equals 760 torr. And these are exact numbers, 3 significant. My answer is 3 significant. Don't put millimeters or torr here. It has to be pressure in atmospheres. Other mistakes students make. They see the temperature here and put it in here. No, you're always going to get degrees C. You have to convert it to Kelvin. And important information, test number 3. I remind you Kelvin equals degrees C plus 273. Here's degrees C. 273 is the exact number. When you add, you get the same number of significant figures to the right of the decimal as the number with the lowest. 273 doesn't figure in because it's an exact number. 1 past the decimal. Here is the correct answer. That's my temperature. Now, final mistake students make, N. They put the weight in. No, N is moles. And how do you determine the moles of CO2? Everybody see important information on their screen? Thank you. All right, 1 mole of a compound equals, and this is test number 3, important information, the molecular weight of that compound in grams. And the molecular weight of that compound is the sum of all atomic weights. So if you look over here, I'm trying to go from grams of CO2 to moles. Moles go on top when you use your good buddy, your good friend, unit analysis. Grams go underneath. And now, how do we get these numbers? 1 mole of a compound equals its molecular weight. What's the molecular weight of carbon dioxide? CO2. I have this right over here. 1 carbon, carbon to 3 significant figures. The atomic weight is 12.0. Oxygen, there are 2 of them. 2 times the atomic weight of oxygen is 16.0 to 3 significant figures. Do the math, add it up, and the atomic weight for CO2, proper significant figures, is 44.0. And this is for 1 is an exact number, but 44.0 is 3 significant figures. Therefore, my answer is 3 significant figures. Now, put the things in. N is moles. We calculated it, 1.97. R is the universal gas law constant, which is also an important information, test number 3. Here it is. Temperature in Kelvin, there. Pressure, there. 3, 3, 3, 3, 3 significant figures. Now, if you notice, let me move this, you see both ways. You can either round off at the end, which Dr. White doesn't like to do, but you can, or you can round off at each step. On a test, I will calculate both ways, and sometimes they're the same, sometimes they're different. If they're different, guess what? Either one would be correct. All right, let's look at number 11. What I'd like you to do is read the problem, find out what are you being asked to calculate, what are you given, and then just solve for the variable you're trying to solve with using the formula you should use. Hint, ideal gas law. You don't have to do all the conversions now, just do that. Remember, all I'm asking you to do is figure out what are you given, what are you being asked to find, use an equation to solve that variable just with the letters, and then I'll take over. I should do this. Everybody read the problem already? Yeah, I'll go back to it. Remember, don't do the conversions, just calculate what are you being asked to find and what are you given. All right, I think everybody's done with what I asked you to do. Let's see if you did it right. When you see a problem, the best way is, first of all, identify what are you being asked to find. What is the volume of the nitrogen in the tire? And that's what you're trying to find, V. You're given the weight of the nitrogen. You're given, it's at 705 torr, and you should know torr is the pressure. You should also know 26 degrees C is the temperature, and you would be given an important information, R. And therefore, notice you have a gas, nothing is changing, therefore, PV equal nRT. What are we solving for? V. How do we get it alone? Divide P on this side to get rid of P. Anything divided by itself is number one, which gives you V. Whatever you do to one side, you have to do to the other. I did. Cancel this out, you get V equals nRT over P. Now, remember, N has to be in moles, and you go from grams to moles here using a unit analysis. Remember, 1 mole equals molecular weight of that compound, and for nitrogen, 2 times 14, 28.0. P is in atmospheres, and we just did this, and you know how to go from torr to atmospheres. Temperature, degrees C in Kelvin, degrees C plus 273. Here's our number, we get 299. And now, once you've done that, you can put in your numbers, and the answer is 24.3 liters. And that's what your car tire is. It turns out, I looked it up, that's about the volume of a normal car tire. So you don't have that much weight of nitrogen, but because it's a gas, it expands. Now, instead of rushing, let's take a 5-minute break now. If I look at the clock, come back at 9:51. That's on your watch. It says 9:51. I'll see you in 5. I'm going to go stretch. Time to start again. Everybody back? I hope you are. All right, let's continue on. Let's do one more problem from PV equal nRT. And one thing I should point out, one of your colleagues I forgot which problem, I made a math error somewhere. I think it might have been here, but I'm not sure. So if you see a math error in one of these, I set it up right, but once in a while, even Dr. White makes a mistake. All right, let's look at number 9. Can everybody see number 9? Thumbs up, people, thank you. All right, now, again, 15 points. What is the weight of 5.77 liters of oxygen gas, O2, at 101 degrees C, 678 torr? What are you being asked to find? Weight, which is grams in our class. What are you given? The volume of a gas, the temperature of a gas, the pressure. And you need PV equal nRT. But oh no, wait. There's no grams there. There's pressure, volume, N is moles, R is universal gas law constant, T is temperature. So what do? You need 2 steps. The first one you find and solve for moles, N. And then you convert moles to grams, which hopefully you learned, and I think most of you did, for test number 2. And you'll need it this test too. And that was an important information. We've already done grams to moles, but you should know how to go moles to grams. So in step 1, I want to solve for N. How do I do that? Well, I've got to get rid of R and T. How do I do that? Divide by R and T. Whatever I do to one side, I have to do to the other. And when I do that, R and T cancel out. I'm left with N equal PV divided by RT. And I'll rewrite it, and I did. N equals PV over RT. Now remember, pressure has to be in atmospheres, and we converted from torr to atmospheres. Next, volume. By the way, volume I'll always give you in liters. You don't have to go from milliliters to liters. That's my gift to you. A little gift, but still a nice one. And therefore, we can put in V 5.77. R, universal gas law constant, is this. And temperature, you can't use this number. It has to be in Kelvin. Temperature in Kelvin, degrees C plus 273. And therefore, we have 101 plus 273, 374. We do that, and we get 0.170 moles. Now, are we done? No, we want to get 2 grams of oxygen. And how do we do that? Second step. I have grams of moles of oxygen. I want to get the grams of oxygen. I use my good buddy, my good friend, unit analysis. Whatever I'm trying to get to goes on top. Whatever I'm trying to get rid of goes underneath. Where do we get this? 1 mole of a compound equals its molecular weight. That's an important information. Test number 3. And what's the molecular weight of oxygen gas? Well, it's the sum of all atomic weights. 2 oxygen, each oxygen is 16.0. And now that's 32.0. So for every 1 mole, 32.0 grams, multiply it, and you get 5.44 grams oxygen, and that's what you get both ways. And that's how you do PV equal nRT. Now, one of the things I didn't do, bad Dr. White, is have Dalton's law. Let me check. Everybody see Dalton's law? Thank you. And Dalton's law of partial pressures is the total pressure of a mixture of gases, P total, is the sum of the partial pressures of each gas in that mixture. Partial pressure like P1, P2, P3, and so on is the pressure of that gas in the mixture if it were alone. So Dalton's law is P total equal P1 plus P2 and so on. And you have to wait while I write out the problem, just like if we were face to face. And it's time for Dr. White to decode my handwriting. And the question is 3 points. What is the pressure of a mixture of helium, He, and Ar, argon gases if the partial pressure of helium is 101 torr and the partial pressure of argon is 606 torr? And important information, P total equals P1 plus P2 plus P3 plus Pn. And I'm going to let you do this all on your own. Boy, this problem set stuff is thirsty work. And while you're doing that, and the votes are coming in. And it looks like everybody's done, so let's get going. All right. First question is, what is the pressure of a mixture? And that's P total. And that's what we're being asked to find. What are we given? The partial pressure of helium is equal to 101 torr. The partial pressure of argon, Dr. White worked with a lot of argon in grad school, so it's a good old friend of mine, is equal to 606 torr. And therefore, what do we use? Dalton's law of partial pressure. In this case, the total pressure, P total, is equal to the sum of the partial pressures of the gases. Partial pressure of helium plus the partial pressure of argon. And that's equal to 101 torr plus 606 torr. Keep an eye on me so I don't make a mistake. And that's 707 torr. And that's how you do Dalton's law of partial pressures. And with that, I will ask, are there any questions about gases? Check out the chat. Listen to my speakers. Well, in that case, it's lab time. And today's lab deals with molarity. And you can download it from Blackboard. Hi, everybody see Molarity Lab on your screen? Thank you. Thumbs up, people. All right. Molarity is an important concept in chemistry. It's defined as molarity, moles of solute per 1,000 milliliters. You notice Dr. White got fancy and used my drawing software to do this formula. And it's written as X capital M compound. So if you have 9.45 capital M NaCl, don't forget to pass the NaCl, bracket AQ close bracket solution, then you have 9.45 moles of sodium chloride per liter or 1,000 milliliters of solution, and the AQ indicates the solvent is water. In this lab, you'll be making solutions with two different solutes. You'll be calculating the molarity of each solution. Now, normally, this is conducted in what's called a volumetric flask. And let me show you picture one first. Everybody see the glassware on your screen now? Uh-oh, well, I'm glad I asked. Now do you see it? Thank you. These are volumetric flasks. If you look here, there's a line on the neck. And what you do is, and if you notice here, this is 100, this is a 50, and these are smaller. These are probably 1 liter right here. These could be 500 or, yeah, 500. They come in different sizes, usually multiples of 5 or 10. And what you do is you put in some water about halfway, then you put in your solute, then you fill the water or your solvent up to this line, just like a graduated cylinder. And these are accurate to 0.03% of the volume, which means they're very accurate measurement, because on 100 mil, your accuracy on a volumetric like this should be plus or minus 0.03 milliliters, which is quite accurate. And you then put the stopper in after you filled it up to here, shake it up, and you've made your volume, you've made your solution. Now, a number of years ago, when I was working and had a lot of expendable cash, I went on eBay and started collecting cute glassware. Can everybody see this is a 25. I've actually got a smaller one of 5. I got a glass bead in there. but you'll see there's the line right there, and you fill it, put some water, put your solid, if it's a solid, if it's a liquid, and you fill the water up to here. You've got a glass stopper, you take it, you mix it, and now you got your solution. But isn't that cute? Now you know I'm a chemist because isn't that cute? It is, which is why I bought one. In my living room, I have a couch table that has all sorts of chemical stuff, plus the balance from my father's drugstore and his weights too, something very dear and near to me. All right, let's go back to the lab. That's not the lab. Now, in the simulations from Beyond Lab Z, they don't have any volumetric flasks. What they do it is in a graduated cylinder, which you normally wouldn't do, but for the most part, their simulations aren't that bad. So I'm not going to complain. Last summer, we used a product called Labster for 1211, and excuse me, it was awful, 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 awful. I keep on going awful because I don't want to use any nasty words that I could use. And I even had a lot of problems with it. If I have it, you can imagine what the students had. All right. Now, some key formulas you'll need for this lab. Moles of solute. Oh, you know how to go from grams to moles. Grams of solute per 1 mole divided by the molecular weight of the solute. And you know how to calculate it. Now, for this one, we're not going to be using a graduated cylinder that's 1,000 milliliters. So how do you go from moles of a solute per less than 1,000 to get the molarity? You take the moles of the solute, multiply it by 1,000, and divide it by the milliliters of solution in the graduated cylinder. For this lab, that's 50. Now, here's the procedure, and hang in there. I'm going to log into Beyond Lab Z. All right. On your screen, you should see where it says Beyond Lab Z in Chemistry. Click on Open. Now, does everybody see Welcome to Virtual Lab, Chem Lab on your screen? And up here, you normally would click on like gases and organic, but today's lab, we're going to do something different. Watch carefully, and it's in the instructions. Right here where it says worksheets, where it says reactions and stoichiometry, click on that. And then you have further choices. And there's a bar here you can slide down. If you look here near the bottom, we have creating a solution of known molarity. Notice the top one, if you look at the column on the right, says sample of ammonium chloride. The other one would be sample of baking soda, which is sodium bicarbonate. You're going to do both. Let me show you how you do this. Click on this. So everybody see the Beyond Lab Z Lab? All right, it's already put out the ammonium chloride. Now, watch closely. Click, first of all, we need a beaker. So I'm gonna open the drawer. Let me move this up here. Take a beaker out and put it over here in the white circle. And I'll close my drawer so you don't get hurt. Walking into a drawer is not fun. Now, click on the balance. And now it's closer. This is called weighing paper. You never weigh a solid right on the pan of the balance. So we'll take it and put it on the balance. Now, notice there's a weight on the balance already. What we need to do is click on tare, and it's 0. And this is also in the instructions. Now, if we click on the bottle here on top, we take the top off. Now, here's a spatula. Sometimes it doesn't want to do this for Dr. White. We'll take some and we'll put it on there. And it doesn't want to do it. Hold on. Like I said, I had trouble yesterday. I'm going to talk to, I know people have Z now. No, let's try it again. Two days later, there we go. You guys center it just right. Now, record the weight here, because that's the weight of this case, ammonium chloride. Now, pick up the paper and you'll put it in the beaker. Now, where it says zoom out, we will. And if you don't catch this one, it's in the instructions, but you can come back and look at the video. This should be posted sometime this afternoon. And now we have over in the left upper right-hand corner, see how you have graduated cylinders? Here's the one that's 50 and it's empty. You'll pick up the beaker, hold it over here, and that's funny because it's solid. It shouldn't sound like a liquid, but that's the mistake they have. Now, you'll come over here, put it under, put some water in, and when it's full, it comes back. And now you know you have 50 milliliters. And that's part 1. And part 2, you'll do the same thing where you'll come over here and you'll do it with sodium bicarbonate, baking powder, baking soda. And if we open it up, does everybody see the baking soda on your screen? Now you do the same thing with that. If you notice, I have these steps, and then you'll repeat steps 3 through 13, doing it with the baking soda, sodium bicarbonate. Now, over here, when you do the ammonium chloride, I have a nice table for you. Weight of sample, the volume, moles of solute, and molarity. And you use formula 1 and 2 up above to do that. And then I've got some questions. Yeah, I do. And that's today's lab. And that's how you do molarity. And hold on, tea break. And with that, I'm done. And we're done for today. Important thing, don't forget, Monday, I will be going through the solutions problem set. I highly recommend you do them before I do. So if you have any questions, you can ask me. Don't forget, next Wednesday is test 3, and the information about test 3 has been already emailed to you, and it's also on Blackboard as an announcement. And with that, I'll stick around for a couple minutes in case anybody has any questions, but I can say goodbye. And it's time for my world famous goodbye to my class. So, class, gang gesund, goodbye.